All right, so a big thank you to the organizers for this opportunity to present some research that I've been doing, which is based on a paper from some years ago and a more recent one with my master's student, Hector Dlamini, at the University of Pretoria. And just because Pretoria is perhaps not very widely known in our community, let me point out where it is in South Africa. And it's a city which is famous quite a bit for its jacaranda trees that bloom in the spring, so around October, and it's quite pretty. That's just it's always a very sunny place, so it's quite a nice place to work. So let's talk about what I want to discuss, and it's going to be quite similar to a couple of talks ago, the discussion of the lambda deformations by Konstantinos Zoubos. So I don't have to repeat how important the n=4 Springer-Mills theory is in our field. It has so many interesting properties like perturbative finiteness, non-perturbative finiteness, with which it's a full 4D superconformal field theory. It plays a role in the DCFT correspondence. It's planar integrable. Planar amplitudes have very interesting structures. And of course, I'm not giving references here because it would just be too many to put on this page. So the question is it a unique theory with all of these features? Well, that's probably yes. But are there other theories which perhaps share some of these features, but not some other ones of these features? So the main motivation of what I'm going to discuss is how does this knowledge that we've accumulated for the n=4 theory, and in particular in the context of integrability, which is somehow where I come from, how does this help to understand more realistic theories? Okay, so similar motivation to what Kostas discussed earlier. So I'll be looking at marginal deformations of n=4. So these are theories which are as close as possible to the n=4 theory, but unlike the previous talk on lambda deformations, my focus is going to be to preserve some supersymmetry. So I'll be preserving some conformal invariance, so I'll be looking at marginal deformations, and also I'll be preserving some supersymmetry, so in particular n=1. What I will not care too much about preserving is integrability. Although in the end, of course, I'll have to settle for it at this stage. Let me remind you how the n=4 Springer-Mills action looks like in superspace. The focus of this talk is going to be the superpotential here. n=4 contains, as you know, three complex scalar fields and some fermions, and this is the auxiliary field in the superspace formalism. So in terms of these scalar fields, or actually in terms of these superfields, fine, the superpotential is written like this. And in particular, if you look at it, well, okay, I'll be focusing a bit on that. I'll be saying a few more things about it. But in general, you can think of how can we marginally deform this superpotential so to get a more general theory, which has less symmetry, but preserving at least classically conformal invariance. And you could write the most general somehow up to sort of redundancies. This is the most general thing you can do. Add another term which contains a symmetric tensor. Now, of course, not all of these are going to be exactly marginal, and we want exact marginality. So you can study which ones actually are exactly marginal. This was done in a kind of exact, sort of non-perturbative way by Lee and Strassler in '95, and they came up with this. So there are two things that you can do, basically, to the n=4 superpotential to preserve exact marginality. One is to convert the commutator that was in the previous slide to a Q commutator. So you add this Q here, and instead of and if Q is not equal to 1, then this becomes this is known as a Q commutator. The other thing is you can add this cubic term, okay, but only in this particular combination of the fields. Now, if you take Q = 1 and H = 0, then you fall back on n=4. Now, if of course there is a function, you don't actually know what are the values of kappa, Q, H, and the gauge coupling, which is also part of the Kähler part of the Lagrangian. You don't know what is the actual combination which keeps the thing exactly conformally invariant. There is a function of all these couplings, and at one loop, this function looks like this. And let me also emphasize that n also plays a role in this function. So, you know, at the non-planar level, it looks different from the planar. The most studied case is the case where you take H to be 0, so you forget about this part, and you take Q to just be a phase, e to the high beta. Okay, this is known as the real beta deformation. So I'll have a lot to say about that. Well, actually, already now. So how do these least rational theories, I'll call them, which parameterized basically by Q and H, how do they compare to n equals 4? Well, they're supposed to be conformally invariant. The DCFT dual, of course, is known for n equals 4. That's just ADS5 courses 5. It's type 2B string theory on ADS5 courses 5. For the least rational theories, only essentially the real beta case is known, and that was studied by Lund and Maldacena in 2005. Well, actually, the complex beta is also known by T-duality and by S-duality on this background. So actually, I should have said really complex beta. But not any of the H deformations. Okay, so if H is non-zero, we don't know the full background, the full dual background. Although it should exist, it should be ADS5 times some deformed sphere. Planar integrability, yes, for n equals 4, basically only real beta. Now, what does this mean? I'll explain soon. There are actually some theories that you can get by doing unitary transformations on the real beta case. So they're kind of unitarily equivalent, but although they look quite different. I will be talking about one of these.
Normally there's two choices, right? Either real or root of unity.
Sorry?
It can be either real or root of unity.
You mean beta?
Yeah.
Yeah. So beta, I'm taking beta here. So if beta is real, then Q is root of unity.
Okay.
Yeah. Q is root of unity. If beta is imaginary, then Q is real.
Okay.
Okay. So but Lund and Maldacena, of course, looked at both of the general case here. Okay. So, but not by the methods I will discuss. This was done using S-duality of type 2. So let's take a closer look at the symmetries to understand what makes this beta deformation so special. So let's go back. Okay, so we have this superconformal group. This you can write as an SU4, but in n equals 1 superspace, you only actually see this part, the SU3 times U1. And this you can see very clearly here. If you write this like that, then this epsilon is just basically the invariant tensor of SU3. So if you do a transformation phi to U phi, then this just gives you the determinant, and you get that it's the same. So that's how we see that there is an SU3 symmetry. Of course, there's also U1, which is kind of obvious. Now, how about least rational? Here, this is the superpotential again. I'm just rewriting it. Naively, it seems that there is no SU3 left. Because, of course, once you start putting these things, you cannot just do an SU3 transformation on, because this is not epsilon ijk anymore. So you have some Z3 symmetries. They combine also with another Z3, which is inside this U1 to some non-abelian group, but discrete group here. Anyway, but it seems that there is actually no SU3. SU3 is broken. So there was an SU3 times U1. The U1 is still there because it's implicit in this superspace notation. The SU3 is gone. But for real beta, now if I forget about this and I take Q to be a phase, then I enhance this to U1 cubed, and that was instrumental for Lund and Maldacena to get the dual background because they needed to do T-duality, and they needed these U1s. So is this everything? What we claimed in this paper with Teresa Monson was that actually, if you think about it a bit more closely, this group is not, this SU3 is not broken. It's actually deformed. And how is it deformed? In a quantum group sense. So we claim that you can still take our phis of n equals 4, transform them with a matrix. This matrix I write like that, and these components they satisfy these relations, which are hard to read, I'm sure. But what it means is that these t's, so if you take this T11 and T12, it doesn't commute, it's not the same as T12, T11. Unless you take Q to be 1. Yes?
And the delta 27 was the deformation of the wild group of the
I think it's related to the wild group. But it actually contains, it's actually SU4 because it contains a bit of the U1. So it's SU3 times U1. It contains a bit of that. I showed it in the previous. We can do it. Okay, so what am I doing here? I'm taking this matrix, but this is not an SU3 matrix anymore. This matrix depends on operators here, which do not commute with each other. They're not numbers. Okay, so this is not a Lie group, because in Lie group you have matrix multiplication, but your matrices just have number components, C-number components, not operators which are non-commutable. So, okay, I'm going to go very quickly through this slide. I just want to focus on one thing about quantum groups, and I don't expect you to follow it very closely. I mean, all this discussion you haven't seen before, but there's a concept of a co-algebra, which is basically the same thing, very similar to an algebra, but instead of the product of an algebra, which takes two copies of a vector space to one copy, the co-product does the opposite. And maybe that's, for those of you who haven't worked with co-products very much, this is what we do when we look at, say, two states in quantum mechanics, and we want to act with the spin, for instance, and we write this as S on the first state times the second one, plus the first state times the spin acting on the second one. So this procedure, really, here we should have put the co-product and claim that the co-product takes this form. So it acts like the operator times the identity plus identity times 4. So whenever we're doing quantum mechanics and we act with spins on a multi-particle state, then we're actually implicitly using co-products. We don't emphasize it because this is called a trivial co-product, and that is the co-product of which basically leads to a Lie group. But if now this became suddenly non-trivial, so suppose I put a Q here, for instance, then you can see that this becomes non-commuting, so I cannot just exchange my two parts. And so it depends, so it's a non-commuting co-product, and I get a Hopf algebra instead of, or what I would call a quantum group, instead of a normal Lie group. So that's one way of motivating why I'm using co-products here. So anyway, these are some consistency conditions. Let me just focus, okay, so a Hopf algebra, just to give a definition, is defined like this, where you also need some element called an antipode. It has something to do with an inverse operation. But the important thing from my perspective is that you can construct Hopf algebras using a matrix R, which has 4 indices. It acts on 2 copies of my algebra. But a matrix, of course, has 2 indices because it acts on 1 copy of some vector space. This has 2 copies of that, so it acts on 2 copies of a vector space. And this relation here is called the RTT relation, derived by Federer speaking Tartajan in 1990. And it gives you, you can construct the Hopf algebra if the R matrix satisfies what is known as the quantum Yang-Baxter equation, okay, which I write in indices here, in case this notation is unfamiliar. Okay, so if you have this YBE, then you're guaranteed that this construction is going to work, in the sense that, well, you can always do this, but your problem is that, suppose now this defines quadratic relations between the T's, which are the ones I showed a few slides back, the ones that you probably could not really read. But now, of course, you want to have cubic relations and higher order relations. Now, who tells you that all these relations are consistent, or whether associativity is going to force new relations at cubic level, which were not there at the quadratic level? If this keeps happening, you'll trivialize your algebra. Your algebra is going to, your operators, the only solution to this will be that T is the identity.
Sorry, this quantum group based on SU3 is a 1-parameter deformation.
In general, it's no. The one we derived is a 2-parameter deformation. It depends on Q and
relate
H.
to just beta, which is just 1 parameter.
Sorry.
You relate to beta. Which
Yeah,
is
Q is e to the I beta. So that's
Yeah.
1 parameter.
Yeah.
But in what I showed before, there were actually, so these relations, there are actually 2 relations. There's Q, which is e to the I beta, and there's H.
Okay, so at the very end you will give just H and Q in terms of just B.
That's what I'm going to do now, but in general they're different. These are independent. Yeah? These are totally independent numbers. But in this talk, yes, I will be doing that for simplicity, and because I don't know how to do the general case. So let me focus on, okay, so I was just saying that you need the YB to make sure it's not trivial. But what we did in that paper, we showed that actually this all works fine, and we do get a Hopf algebra. I'll say a few things about that in a second. And if this condition is satisfied, we call it a quasi-triangular Hopf algebra, and that's what generally in the literature is known as a quantum group. So R, this R matrix, you can see it from here, because these are just the same thing, but just commuted around, or you can see it in this slightly more abstract relation. The R matrix is what somehow controls the non-commutativity of, if I write like this, of the co-product. So when I was saying that you can change this co-product, basically it's the R matrix that decides somehow how do the different orderings relate to each other. So for the general least rational deformation, how do we get this R matrix? Well, we start from the spin chain Hamiltonian, which I have not discussed spin chains at all, so just take it as given. It's basically, you can just read it off from the Lagrangian. These are somehow the coefficients of the scalar fields. There's a quartic coupling in the Lagrangian of the scalar fields. And Reuben showed us how you can read off the one loop spin chain Hamiltonian directly from that. And then you just basically, the R matrix is the identity minus this H, and then some indices swapped. And this is the final form of the R matrix. If you use this and you apply the R to T relations, then you get these matrices T that I was describing earlier, which are the correct ones to rotate the phis and for the full least rational deformation, so preserving the full solution. Okay, so this depends on Q and Q bar, and also on a D, which is this combination, and an H. Any questions about this?
What is H?
Huh?
What is H?
This H is this second least rational, so it's this H here.
Oh.
Okay, so everything, so kappa is something overall, so my algebraic structures are going to depend only basically on Q and H. These are my two independent parameters.
Maybe, sorry, maybe I misunderstood the point. So not just the real beta as can be embedded in a quantum deformation, but the full
Yes.
Ah, okay.
Yes. No, real beta, of course, Luna-Maldacena and Reuben and Bizert, they have already shown how that works.
Okay.
Because just basically adding phases everywhere. So, so there's a star product that Luna-Maldacena wrote down, which is basically some phases. So that's part of the story, but of course we were trying to get the algebraic structure for the general case. And we did. So now the point about this is this R matrix does not satisfy the Young-Baxter equation, this quantum Young-Baxter equation. If it does, then we recover the known integrable deformations of n equals 4, in particular the beta deformation. But there are some other unitary equivalent ones. Generically, we do not have a quasi-diagonal Hopf algebra, but is it still a Hopf algebra? Which means, because then the RTT relations do not guarantee that. But what we did in that paper from 2008, we showed that this is the case because we explicitly constructed the antipode, we constructed something called the quantum determinant, and we showed that it is a Hopf algebra consistently up to and including cubic level. We didn't go higher. So we still have the danger that this whole construction might get trivial if you start looking at higher order. So we haven't analyzed this in detail, but in this paper, in this talk, we want to do something different. So that was back then. Now, what was the new interest I had in this is, well, we are claiming that, my claim is that these least rational theories have more global symmetry than is naively visible if you look at the Lagrange. So you have to think in a quantum group sense to see this global symmetry. So the Lie algebra, this SU3, became deformed to a Hopf algebra. So how do you work with this? And in particular, I mean, if we're trying to find ATSCFT duals, because that's also one of the goals, to construct the duals, how is this visible on the gravity side? Now, of course, the gravity side should just be a smooth manifold. It's some deformation of the sphere. There should not be any quantum groups there. So how is this encoded, if it is encoded on the gravity side? Yeah, and can we construct a solution generating technique? So first, I'm going to focus on the integrable cases. And that's all I can do now for a reason I'll explain. But the goal is, of course, to do this for the full story. So I'm going to find this integrable, my theories as twists of the n equals 4 structure. So I'm going to introduce a new element here, which is called a Drillfield twist, which we also kind of, by abuse of notation, call a Hopf twist. As opposed to something we will call a quasi-Hopf twist, but I'm not going to go into that in this talk. So what do you do with this? If I take a coproduct of some algebra, and then I take f being an element of C times C of the algebra times the algebra, and it's invertible, then I can define a new coproduct. That's what Drillfield showed us. And I can define also a new R matrix. So basically I can twist the R matrix. This is not a normal sort of symmetry transformation. That would be if this would be F12. This tells us which sort of elements in the product of the Hilbert space you act on. So this is not a symmetry transformation, because that would be trivial, of course. Then that if you start with a Lie group, you end up with a Lie group. Obviously, if you do a normal transformation like that. this actually can take you from a Lie group to a Hopf algebra, or from a Lie algebra. And in general, this F, we would like to satisfy something known as a co-cycle condition. I'll say more about that in a minute. For n equals 4, because n equals 4 is, the symmetry is SU3, so it's a Lie group, then this R is just trivial, it's just a identity. So, and of course, the co-product that we get from this R is commuting, and you get SU3. But we're going to twist it using this, and we're going to get some new co-products and new R matrix. So let's focus first on the beta deformation. So if you take the general R matrix I had before, this is how it looks for beta real. It's very simple, diagonal, and it satisfies the Yang-Baxter equation, and you can see that it has a lot of symmetry. But for us, this is a little bit too simple, because of course you have the U1s here, and they're explicitly sort of visible. So we would like to somehow to practice going to non-integrable cases. We would like to find some theory which is in the middle. Still integrable, but more complicated than a real beta. Our problem is that that thing doesn't exist. So it turns out that the only integrable deformations are the real beta and theories which are unitary equivalent. So we'll choose one of those because we think it's still relevant. So let's take this theory here. I'm taking Q to be 1 plus W, where W are a real number, and H to also be W. So I'm relating Q and beta as was suggested. You can do unitary transformation to take this theory, this superpotential that we get from here back to the real beta, but I'm not going to do that. I'm not going to take advantage of this fact because I want to act as if this theory is a fully non-integrable case. But still, somehow it will be simpler than the general situation, as I will explain. This is the R matrix. You can write it a bit more compact using some matrices. These are some kind of shift matrices, U and V, which is U squared, so you can write it in a nice form. And this is the twist that would give you the beta deformation. So back one slide. So this you can write as, this thing you can write as e to the I beta over 2, H1 times H2, or these are Cartan elements of SU3. So this is obviously an abelian twist, so because these H1 and H2, they commute. For the W deformation that I just defined, the twist looks like this. You see it's not diagonal. And you can write it a bit more compactly like this. But because these matrices V and U, they commute, this is also abelian. So again, we're kind of trying to fake somehow a more difficult theory so that we can get some experience in applying this. And so let's take this and let's go back to how we can make this sort of, how we can reasonably apply these algebraic ideas. So it's often convenient to work with star products. So we can define a star product using this fact here. So let's focus on this formula here. G is an element of the algebra. X and Y are elements of the module that the algebra is acting on, the representation space. So back to my quantum mechanics, these are the space of states. This is psi1 and psi2. That's the X and Y. G is the spin. Okay, so the element of the algebra that acts on these states. The thing is, this has to act as a derivation, and if you sort of expand this out, what are we doing algebraically here? We're actually using M, which is the product in this module, and we're using delta, the co-product of the algebra. I'm not going to follow through this, but I think you can imagine that if now I start twisting my co-product of my algebra, then the product on the module also needs to be twisted, otherwise you'll lose your derivation property. Okay? And this you want to have. You want to act as derivation on your space, representation space. So there's a standard, in deformation quantization, there's a standard way of dealing with this. So you twist also the module product, which basically is the product between my states, my psi1 and psi2, to account for it. And we call this our star product. If I choose a basis for my module, which is these zi's, then you can also put indices there, because everything is in the fundamental, and it depends on the twister. So these are kind of our new formulas for how we can act. You have to be careful with associativity, because once you define quadratic equations, then you can go cubic, and you get two different forms for the cubic. products. Now, if you don't have this co-cycle identity, which I discussed earlier, then these are not going to be equal. This is not associated. So the general case is that we're twisting to a non-associative algebra. Because we don't yet know how to deal with this in good enough sort of confidence, we are going to focus on integrable twists, where these two things, because of the quasi-triangularity condition, these two things are equal. So we can just have one unique answer for a cubic product, regardless of the parameters. So that's what So that's why we're forced to somehow, for now at least, for this talk, I'm focusing only on this beta and this W theory, because these are integrable cases and I don't have to deal with non-associated. Although the goal is to look at the more general cases and deal with it eventually. So by explicit computation, you can see how this product acts. So you have to put parentheses everywhere, stars everywhere. And what you find is that if I take my least translucent potential and I put stars everywhere in my product, and I expand this out using this relation, indicates to retrace, then I get just n equals 4. So basically this shows somehow you go from n equals 4 to the this translator case. And actually, even better, we're going to define the inverse star product, just with an f here, where if we just focus here, if I take the n equals 4 superpotential, just commutator, and I put in this particular star defined like this, I can explicitly show that I go from n equals 4 to the general, in this case, for the W deformation. It's the same for the beta deformation. It's actually the same for everything once you know the twist. But the problem for the non-integrable cases is that this, you have to be careful where you put your parentheses, because it's not associated. But here we don't have to worry about where to put the parentheses. Great. So we can also go down to first order. This will be useful in a second. So we can define the commutator to first order by some matrix theta, by expanding. This is the classical R matrix. The twist always gets expanded as in terms of the classical R matrix. And this we call the non-commutativity matrix, and these are the forms it has. They have been studied, some more general cases, studied by Colaxisi in 2006, of how they look for the beta, this real beta, and this is the W case. Okay, so I'm almost there. I've understood how, this is already quite some progress because we did not know anything about these twists before. So now we understand how to construct the Hopf algebra using this twist. We can define an all-order star product, because there was nothing stopping us in integrable cases. This was, so if you ask me what is the star product between 6 z's, I can give you the full expression. It's not an expansion in order by order in the parameter, it's the full thing. But sometimes you need to expand the first order just to produce known results. So let me switch now, in the next 4 minutes, to the gravity side. How do we use this star product we defined on the gauge theory to see some indication of this quantum symmetry on the gravity side? To do this, we use the framework of generalized complex geometry, which I will not have the chance to discuss. Let me just say that it unifies complex and symplectic geometry. It's very natural from string theory because it deals with the metric and the B field on equal footing. And roughly we consider structures on the sum of the tangent space and the cotangent space of a given manifold. And the structures I'm talking about are these iotas, which are contractions, and these z's, which are forms. So my basis for this space is basically, vectors plus forms. So I get for a 6-dimensional space, because I'm working in type 2B and I have T3 branes. So I'm worrying about the 6-dimensional transverse space to T3 branes. I get a 12-dimensional generalized space. So anyway, I won't say too much because of lack of time. But roughly, if I'm looking at C3, that's my transverse space in flat space. C3 you can parameterize with the holomorphic form and the Kähler form. And the construction of generalized complex geometry defines something known as a pure spinor, which is a multiform. If you look here, I'm adding a scalar plus a 2 form plus a 4 form plus a 6 form. This might seem strange if you haven't seen the formulas before, but it's consistent. So this describes if it satisfies some compatibility conditions, like this, they have to be closed and have to satisfy some relations in terms of some inner product, then this defines an n=2 background for you. So let me just give an example. For flat space, this is how the generalized metric looks like. It's defined in terms of some complex structures, but you can, once you know the pure spinors, everything follows. So you can reach this point just by algebra, once you have the pure spinors. And flat space looks just like this. So you get you get a total dimensional space where the 6-dimensional metric is this. This is the usual metric of C3. Okay, just maybe it might be a half because it's complex. Okay, so this and the dilaton is given like we also saw before by determinant of this G. So all I'm going to do now, and I think I'm done, is to twist these pure spinors. And I'm using the same star product of the Gates theory set. Okay? So I found the star product just from Gates theory motivation. Now I'm taking it and I'm twisting the pure spinors. And I find some new twisted pure spinors that I'm doing it, this is general. But if I do it for the W case, that's what I get. So basically I put star products everywhere. I expand out because I know the explicit form. And I get this. And that turns out to be a compatible pair, and I have an n=2 background. Now, how does the background look? You can see if this is the dilaton, it's given by this combination here. I'm not going to explain all the notation. These are quite complex functions of cosines and sines of all the angles in the game, including the, so there's 5 angles because this is a 5 manifold. But the metric itself, the components look like this, and like this, and like this. This is the B field. There's also number 1 field. It's a mess. Maybe it's easier to draw it like this. So basically, what I've done here is I've plotted. I do not know how to make a proper embedding of this manifold in 3 dimensions. That's a complicated construction. But I can plot the scalar curvature of this manifold against 2 of these angles. These are 5 angles. Let's choose alpha and theta, and I can get something like this. And this tells you that this is a deformation of a sphere. If this was a proper S5, the scalar curvature is of course constant. It's 20 over r squared. So this would be a perfect sphere. Now you can see that by deforming it, and this is the deformation parameter W in units of 1 over the radius of ADS or of the sphere is given by this. So this is a proper supergravity background, and which we checked explicitly. So let me summarize what we achieved by doing this. So we found the quantum algebra structure behind the generally structured deformation, and we are claiming that we're just not breaking the SU3, just Q-deforming it. It's a symmetry that appears at the classical level, even though it comes from studying the one-loop spin chain. So but we're claiming this is a symmetry of the Lagrangian, as long as you think of quantum groups and not Lie groups. And for the integrable deformation, we found the explicit star product, and we showed how you can obtain the dual n=1 background. I didn't discuss that, but from the n=2 background, you just have to add d branes to it, take the new horizon limit, and you get the n=1. So that step is easy. So we found a dual background. Is it exciting? Not so much, because it's diffeomorphic to the Riemann-Malthus-Semel case, okay? Because this theory is unitary equivalent. So the next and more exciting step would be to extend this to the non-integrable cases, which will exhibit some non-associativity. We hope the appropriate structure is something known as a quasi-Hopf algebra, which is non-associative but under control. And we would like to also use this to construct the dual backgrounds, which of course are not known yet. We're hoping to also find a relation to other techniques like the lambda deformations we heard about, or these eta deformations, which have also some relevance, although we are not interested so much in integrability, so we want to break integrability. So their approach is more to keep integrability while perhaps breaking supersymmetry around. There's many other questions that we don't understand, but the main motivation that's driving this is to find whether quantum symmetry of perhaps this type or a similar type is behind the perturbative finiteness of the theory. We know that when this is quasi-triangular, then it's behind the integrability of the corresponding Gates theory. But is there a bigger story there that we're starting to uncover? And I hope to report about that at some future time. Thanks.
you use the generalized geometry,
Yes.
and on one side you have some kind of deformation of structure, quantum group,
Yes.
but on the other side you said it's classical. Is that right?
It's a smooth manifold, yes.
Smooth manifold. So is the generalized structure also deformed? Because how do you encode the? Sorry, I missed it.
Yeah.
Just
So
too many
yeah,
slides.
I was going a little bit quick, but of course we don't actually know. We don't have a theory of this. This is a bit empirical. So what we're doing is we're taking the pure spinors, which describe our generalized geometry. These are the pure spinors, and we're just putting a star product there.
So what does that do to the generalized structure?
Yeah, so then, well, I can give you, in the paper we have the forms of all the generalized structures. They become a bit messy, but the interesting thing about this is because these are forms. So the star product on these forms, you get higher terms, but you run out of terms because the maximum you can get is a 6 form. So it's not a kind of deformation where you keep on going. So it's a finite somehow number of terms that you can add when you expand out these star products. So that allows us to just basically get. This is what you actually get, the full story. So you can see that you get new terms. The old thing is here, this is 5. The original thing, you get things at order W, and that's it. Okay. So basically everything else just cancels because these are 4. So it's just a nice way to encode this little deformation of the original structure.
Another question? So in that regard, content group is a really kind of algebra, and we do the implementation. So can we rephrase the homomorphic principle in terms of implementation of quantum field theory and gravity? Implementation of quantum group.
In terms of gravity, as in
Both sides. So both of them have the structure as a modular quantum group.
yes. Well, on the gravity side, I would say, okay, on the Gates theory side, the claim is that yes, this quantum group structure is there. It's a global symmetry of the problem. I wouldn't say that I know the answer on the gravity side. We're doing this just is a hint that the structure is there. But if you ask me about quantum isometries or these kind of things, I don't know what the answer is.
Okay, so let's thank Konstantinos